So I am a first year PhD students at IIT Kanpur. So today is the last session, and I will solve some problems that might help to solve some problems in the exams, and also clearing your doubts. So if you have any questions in the middle, so please reach out to me and ask your questions. So I will suggest you to do the calculations along with me so that you can check the answers and better understand the problems. So any questions so far in the contents, or you can start. Yes. Yeah. So let me share my screen. Screen. The third question. Let me check. Yeah, the ratio of EBC power. This question, right? The ratio of EBC power to the absorptive power for radiation for a given wavelength. Yes. So, what is your questions from this? So, for black bodies, we know that the emitting power and the ratio of the emitting power to absorption power are equal, right? Is that one, right? But here is the given is the unequals. Okay. Yes. So the reason is that when you compare the absorption power and the emitting power, okay, so we tell that they are the same wavelength range and the same temperatures, right? Go to the definitions of the Kirchhoff law, okay, and the Kirchhoff's law tells that at the same temperatures and the wavelength range, the ratio of the emitting power and absorption power are equals. But in this case, that the two spherical bodies are at different temperatures, right? So that's why these things are because they again that these are spherical black bodies. This is not a perfectly black bodies, okay? So that's why they are not equals. At perfectly black bodies, this ratio equals to this ratio are 1, and all are perfectly black bodies at the same temperatures are equals. But here the given is that there are two spherical black bodies, so it's not a considered as a perfectly black bodies at first, and then the Kirchhoff law states that they are equal at the same wavelength and temperatures. Right? Because the Kirchhoff law valid at the same wavelength and temperatures. So if the two spherical black bodies are different temperatures, we cannot apply the Kirchhoff's law and tell that this ratio will be 1, even if for the perfect black bodies, because the Kirchhoff law, the validations of the Kirchhoff law breaks, yeah, according to the question statement. So please go to this of law statements. So that is the main point of this course. So question number 9 of assignment 12. Let me check. Yes, so okay, I will discuss this thing. So this is the, you know the wind's displacement law? Lambda max times temperatures equals to constant, right? Okay, use this and just you multiply, you know the first case the lambda max, right? And the temperature, and the second case you know, okay, so the question number 9 is that the lambda max times T equals to constant. My screen is visible, right? Okay. So in the first case, the lambda max is given 1.5. The unit is the same, so it's the nanometer. 1.5 times the temperature is 1500. And the second case, the wavelength of the maximum emission will be 0.75. 0.75 times T2. So now we calculate T2, right? And then T2 is that 2 times 1500 Kelvin. Is this? So the answer is, yeah. Yeah. Any further questions? Yeah. So it is clear now, right? Okay. So this is wind displacement. We'll discuss this when we solve one problems. So okay, so let's first study the thermodynamics of the problems related to the thermodynamics of the black body radiations. Thermodynamics of black body radiation. So the question is that suppose let's given the Helmholtz free energy for the black body radiations. So Helmholtz free energy is given. If it's given for the black body radiations, means that the photon gas in a cavity, and consider this thermodynamical systems, and the Helmholtz free energy given is 4 sigma over 3c. How to derive this thing? Because when we learn the statistical mechanics, we explicitly derive this formula, but in the context of thermodynamics, we cannot derive this. This is a given. The exact derivations comes from the statistical mechanics. So at this moment, this formula is given, and the question is that calculate the equations of state, calculate the corresponding equations of state for the photon gas, for the black body radiations. So calculate corresponding equation of state. So the equations of state, that means that the functions of P, V and D equals to 0. Some functions of exert volume and temperature equals to 0. So how to calculate? The first is that so once we know the F, to calculate okay, so what what is the differential in X? F, right? So these relations are always useful. So the thermodynamic differential of the potential. So this df is that minus s dt minus dt. So if you use this, then what is the f? F is that minus del f over del t at constant value. So if you want to know the f, so where is the sigma? Is just different both with constants. So sigma is difference. Constant. So now on derivatives, and then we get this 16 sigma over 3c p dt. So that is the entropy is proportional to the temperature Q. So that is the important, that the entropy is proportional to the temperature Q for black body radiations. So these types of variation, that the entropy, energy, how vary with temperatures. So these types of question asked in the, even in the competitive exams, many of the competitive exams ask that the for proton gas, how the entropy vary with temperatures. And similarly, you can calculate the energy E. The energy E is relation is that F plus Ts, because F equals to E minus Ts. So E equals to, so this is the internal energy. So Ts is the entropy, and this is the internal energy. Internal energy E equals to F plus Ts. So now you multiply T and using this formula, so you get that is F minus plus T times S. So we write it in terms of F. So it's 4 times F. Because if you multiply with the T, so this is T to the power 4, so minus 4. This is minus 3F. So now put the formula of F that is given. So again, this, that means the E energy and the free energy are the same temperature difference, right? So that's why called the energy and the free energy. So energy and free energy both are same temperature difference. That means the energy depends on the T to the power 4. Same dependence with the free energy. So this is the internal energy and this is the free energy. And why it's called free energy? So this is again come from the statistical mechanics. So when we learn the statistical mechanics, then it becomes more clear that why it's called the free energy, not the energy. And what is the difference from this? Energy and free energy. And similarly, if we calculate the Cp, let's say the specific heat. Cp. This is daily over delta, the internal energy daily over delta at constant volume. So in the previous we called that this is a U, but here we notation that this is a E, denoted as internal energy. So the Cp is daily delta over V, so this proportion equals to the 16 sigma dq V is what? Just see, there is no 3 factors, 1 over 3 factors. That means that the specific heat Cv is proportional to dq. Yeah, so once you derivatives that, so these 3, okay, so let's do it explicitly. What is the E? So E is that there is a 3, right? So these 3 cancel. Yeah, so now so we calculate entropy from this. So entropy is del F del T over at constant volume. Similarly, if we write down the pressure, P equals to minus can you tell me what is the formula for the pressure from this equation? Use partial difference. No, del F, del V at constant temperature. Because okay, so the F is a function of T and V. So these are the functions, right? So that means when we write the differential df, this is dt and dv. Some quantity there, right? Because f is a function of t and v. So when we write the differential df, it must be a functions of dt and dv. Okay? Then what is the coefficient? The coefficient is the del f del t times t plus del f del v times dv. And in this case constant v, and in this case constant t. That is the partial differences. We write the df in terms of del f del t dt. Okay, it looks like a df again. Plus del f del v dv. It looks like a df. So we can just split in terms of two derivatives because f is a function of t and v. It's not clear, right? So now we compare this equation with these equations. So this is a 1 and this is 2. If we compare, that means that del f del v t equals to minus v. And f is a minus del f del v. So comparing 1 and 2, we get this. So best we can write explicitly in this form and then compare. Yeah, it's clear, right? So now we calculate this p minus del f del v. So once we know the f, so that means the 4 sigma over c t to the power no v there. So now once we know the p and we know e, so that means if we multiplied p with v, right? So this is 4 sigma over 3c e t to the power 4. So this is nothing but the f minus f. So minus f equals to 1/3 e. That means the equations of state Pv equals to 1/3 e. So this is the equations of state. It's the internal energy through the equipartitions of theorem. We know that the E is a function of T, kVt. So that's why the Pv equals to 1/z. This is standard. It's not a standard. Also, is a standard form of the equation of state. For the ideal gas, we just calculate for the ideal gas. So we get that the Pv equals to 230. So here is the difference, that is a 130. For the ideal gas, we got Pv equals to 230. How to know? Because from ideal gas, what is the equation of state? Pv equals to n kVt, right? So now we know that for ideal gas E equals to 3/2 kV, right? The 3 dimensions and the 3/2 kV. So just put it there in terms of it, we get this. And this is for the photon gas, equations of state for photon gas. What is the difference from this ideal gas? So now another interesting thing is that that P pressure, derive this, P is independent of the volume and only depend on the temperature, 4 sigma over 3c T to the power 4. So P is uniquely determined by the temperature only. So pressure is uniquely determined by the temperature only for the photon gas. So this is a study for the photon gas. So pressure is uniquely determined by the temperature only. So that means that E and T are not really independent variables. E and T are not really independent. Now, can you tell me what kind of thermodynamic potential depend on this P and T? The independent variable P and T, because we know that in case of free energy, the independent variable T and V, right? So, what are the thermodynamic potential that is for the independent variable P and T? Okay, so how to construct that? So first we know that, so let's say U is a function of S and V, right? Because the du, so this is the main relations, du equals to TdS minus VdV. So what is the here we denoted that E, right? So d is a TdS minus VdV, right? So this is the main relations. Okay, so we have to memorize these relations. So d equals to TdS minus VdV. So now from these equations, what is the functions of E? E is a function of H and P, right? So once we know that E is a function of S and P, right? Now we construct, let's say F, Helmholtz free energy. How to construct that? F is a function of T and V. So that means if we construct F from E, so by Legendre transformations, that E minus what is the variable changes, S to T, ST. Initially E is a function of S, V, but now we construct a functions that is function of T and V, right? So the S, that means that the S go to T. So by Legendre transformations, you construct that E minus ST. That is the definition, is called the Helmholtz free energy. Similarly, if we construct that, let's say the another function G is P and T. So that means that the both variable changes. So E minus S to T changes, ST, and V to P changes, plus P. Why there is a plus sign? Because P and P are related to a minus. When we increase the pressure, volume decreases, or when we decrease the pressure, volume increases. That is from the physical significance. Why we put here plus sign? Usually there is a minus sign, but if the quantities are related by the physical implications, okay, then we put an extra sign according to your describing of physics. Okay. So what is this quantity G? Yes, right. So this is Gibbs free energy. Gibbs free energy. Now for the photon gas, we see that the P and T are not really independent, right? But in this case, we say that the whatever the quantity that depend on the independent variables, right? So from this, for photon gas, what do we expect? What is the values of G? Yes, because they are independent, right? Photon gas G equals to 0 gives free energy 0. So you can show explicitly how. So once you know the Helmholtz free energy, so Helmholtz free energy given from the statistical mechanics. So we calculate this. So okay, so we know energy, we know entropy, we know pressure. Right? Just derived it here. So this is the pressure, this is the energy, okay, this is the entropy. Just put here, we get that G equals to sigma over 3 so minus 3f equals to minus 3f plus t times f. So times f, yeah. So we can get minus 4f plus 4f and e equals to minus f. E equals to minus f. So minus f. So this is exactly 0. So now if you know the relation that derived in the class, that G equals to nu times N, where nu is a chemical potential, so by and N is the number of photon, photons. In the photon gas, in the cavities, the number of photon is N. So which is not equals to 0. Right? Where otherwise the system is not there. So the number of photons which is not equals to 0. So if G equals to 0, we implies then G equals to 0 implies that mu equals to 0. So that is for photon gas the chemical potential 0. So for photon gas chemical potential equals to 0. Very important. Okay. So these are the things that for the photon gas. So we derive the equations of states. So this is sometimes asked in the exams. So what is the equation of state for the photon gas, and how entropy vary, and entropy specific heat, pressure vary with temperatures, energy, this temperature dependence, and the Gibbs free energy, what is the values of the chemical potential for the photon. Without, you just know that the P and T are just independent, not independent. So the Gibbs free energy, they are not a definable quantity. Means that the Gibbs free energy is not a definable quantity. So now another interesting thing is that so these all the derivations. Okay? So the specific heat and the entropy. So they depend on the power law, right? Power of the temperature. That means that if temperature goes to 0, so this quantity must be goes to 0. Right? So that is the consequence of the third. So what is the consequence of the third? That consequence of the law of thermodynamics. The consequence of the thermodynamics. The first is that the specific heat goes to 0 as temperature goes to 0. Because entropy goes to 0 as temperature goes to 0. Okay. Second is that the thermal expansion stops. Thermal expansion stop. What is mean? The thermal expansion means that the let's say beta P, the expansivity, 1 over V del V del T at constant pressure. So this is goes to 0. Del S del P at constant T, this is goes to 0. Just take that. So del S del P, once you know the formula is, right, we just written in terms of P. Okay, here is the formula of P. And we say that the del S del P is goes to 0 as temperature goes to 0. So this all the quantities that goes to 0 as T goes to 0. Okay. So third is that so no gas remains ideal as T goes to 0. No gas remains ideal as T goes to 0. How do I know? Again, that at low temperatures the ideal gas assumptions is unvalid, because for the ideal gas assumptions we use the kinetic theories. Okay, so the there is no interactions, this kind of things. But when we lower the temperatures and in the T goes to 0 limits, that means the ideal gas model is breaks down. We include the quantum corrections. So that means the no gas remains ideal as T goes to 0. How to prove that? Proves that the if you know for the ideal gas that Cp minus Cv equals to R. Okay. So the Cp minus Cv equals to R for ideal gas. For ideal gas, Cp minus Cv equals to R. Now this R is a gas constant which is not equals to 0. R is a gas constant which is not equals to 0. Then at T tends to 0 limit, Cp goes to 0. The specific heat goes to 0. So Cp goes to 0 and Cp also goes to 0. But R is not equals to 0. So that means this equation is invalid, not valid for as T goes to 0. So that means the ideal gas is not ideal at T goes to 0. But for photon gas, so all the things that specific heat, C, they are perfectly fine for the consequence of the thermal. At T goes to 0, there goes to 0. Because how to derive this thing? It's derived from the statistical mechanics. That means we are going in the microscopic domain. That's why they valid properly. The photon gas is a relativistic gas. Okay, so we derived from the statistical mechanics. These relations derived from the statistical mechanics. So we include quantum mechanics and microscopic picture. That's why they are the specific heat, entropy, all are the validations of the thermal. They goes to 0 at T goes to 0. An ideal gas we derived at higher temperature, room temperature, near room temperature. Kinetic theory is valid for near room temperatures. And that's why the ideal gas is not ideal as it goes to T goes to as in the limits T tends to 0. So that is that. Now we are going to okay. So another thing is that similarly what we did for the ideal gas, the adiabatic compression and adiabatic expansions. So we can also calculate the same thing for proton gas as well. And even if you can these types of questions asked in the exhibitions as well. So for the adiabatic expansions, let's discuss for the adiabatic expansion. Adiabatic expansion. So the adiabatic expansion is that for the adiabatic expansion there is no change in heat for the adiabatic process, right? So that means delta S equals to for adiabatic expansions the entropy is conserved. So entropy is conserved, does not change in the adiabatic expansions. Okay, so this is a reversible. The reversible expansion. So now what we got for the adiabatic for entropy is 16 sigma over 3c VTQ. So if for proton gas 16 sigma over 3c VTQ, which is equals to constant. What do you conclude from this? What is C? What is sigma? Yeah, so C is speed of light. This is a constant. Speed of light is a universal constant. A constant. What is the sigma? Is Stefan Boltzmann constant. It is also a constant. So sigma also a constant. That means that VTQ equals to constant. So we simplify that VTQ equals to constant for adiabatic process. Now from this we can construct what is the adiabatic index. Yeah. So what is the formula for the adiabatic process? P to the power gamma equals to constant. Now I can we can write this in terms of V and T. Have the equation of state. So for this case we know the equation of state T equals to 1/3 E. So E is a proportional to temperatures. So that means T to the power gamma minus 1 equals to constant. Yes. So now compare with this. What is the values of gamma? Yeah, it is correct, right? So again, so for the proton gas, the adiabatic index gamma is 4/3, but in case of ideal gas, for monatomic gas, gamma is 5/3. Right? So that is the so again these types of questions that what is the adiabatic index for the proton gas? So now another interesting thing is that for proton gas, so we learned that the gamma equals to Cp by C. But this is not true for the proton gas. So if you calculate Cp and Cp and divided by Cp by Cp, you never got the 4 by 3. So this is true for non-relativistic gases. It's true for non-relativistic gases. Relativistic gases. Ideal gas, van der Waals gas, all are the non-relativistic gases. But for proton gas, or proton gas, relativistic gas, so gamma is not equals to Cp by 3. The second thing is that calculate the work done. Now, second question is that is calculate work done. Calculate the work done for this adiabatic expenses. Right? Calculate the work done for adiabatic expenses for photons. So now we know that what is the formula for the adiabatic expenses stuff. So let's integrate. Okay, so this is P dV and Pi to Pf. So once we integrate this thing, we get that the Pi minus Pf by gamma minus 1. So this is true for any gammas. But for proton gas, gamma is 4 by 3 and Pi is 1 by 3 Pi. 1 by 3 Pi. This is the equation of state for the proton gas. The equation of state for the proton gas. So we use that this is the 1 over 3 Pi minus 1 over 3 Pf divided by 4 over 3 minus 1. This work done is just minus Kf. That means the energy necessary to produce the expansion extracted from the internal energy of the radiations. The difference in the internal energy is the work done. This is indeed, right? Because in the adiabatic expression there is no change in it. Okay? So like this expression is the energy necessary produce the expansion. So that means the work done is extracted from the internal energy of the radiation. Ei minus Ef, this is the internal energy of the radiation in the initial state, internal energy of the radiation in the final state. So now the work done means that the energy necessary to produce this expansion initial state to final state. So this work done is extracted from the internal energy of the radiations. It is the difference in the energy now we are going to problem is related to the Wind's law. So you know the spectral energy density function, right? Spectral energy density function for black body. Spectral energy density function for black body is also named as the black body distributions. Black body distribution in short. So black body distribution means the spectral energy density functions for black body. So let's say this is for given for nu to in the frequency range. Let's say nu to nu plus d nu in this frequency range. The spectral energy density u nu. So in this frequency range, nu to nu plus d nu at particular temperature d. So again at particular temperature. At temperature T, temperature T, the spectral energy density function, that means the black body distribution u nu is given. How to derive? Again from the statistical mechanics, because wherever the quantum mechanics comes, you need the statistical mechanics to derive this function. So 8 by h by c cube nu cube to the power beta h nu minus 1, where h is a Planck constant, and beta is 1 over k. So kb is a Boltzmann constant. So this formula is given, and c is the speed of light. Speed of light. Okay. How to write the u lambda from this? U lambda, this means that the spectral energy density functions for lambda to lambda plus d lambda. What is nu equals to, what is the relations between nu and lambda? Yeah, so nu equals to c by lambda. So that means d nu equals to minus c over lambda square times d lambda. So the spectral energy density functions equal, that means that u nu d nu equals to u lambda d lambda at same temperature T. U nu d nu u lambda d lambda. It's not that the u nu equals to u lambda. So in the frequency range nu to nu plus d nu, u nu d nu, and in the wavelength range lambda to lambda plus d lambda, the spectral energy density is the u lambda d lambda. So they are equals. So that means that u lambda just put is that 8 by h, right, c over lambda to the power 5, because here is the extra c by lambda square come, right, when we writing d nu in terms of d lambda, and 1 over to the power beta is c over lambda minus 1. This is the black body distribution in terms of lambda. This is the black body distribution in terms of nu. There is the difference. That here is u nu is proportional to nu cube by this, but here is u lambda is 1 over lambda to the power 5. Just put here that the nu cube by c cube is 1 over lambda cube. So here we have put that nu cube by c cube 1 over lambda cube, and here we put nu equals to c by lambda. So beta is c by lambda minus 1. This is the denominator. Now the numerator is that nu cube and denominator is c cube. So nu cube by c cube equals to 1 over lambda cube, and d nu, there is u nu d nu. Now convert d nu to d lambda, so need a c by lambda square. So this 1 over lambda cube multiplied with the c by lambda square, this is c by lambda to the power 5. Okay. So where is the nu cube? At temperature important. Now we plot these things. The interesting thing is that when we plot this thing, so if we plot, let's say u nu as a functions of u. First plot this. U nu as a functions of u, and other side we plot lambda as a functions of lambda for various temperatures. So this type of things even in the various competitive exams actually. So how this distribution vary with temperatures T1, T2, T2. So let's first plot this. U nu at for nu tends to 0 is proportional to nu cube. So nu tends to 0 region is proportional to nu cube. This nu cube, and then sometimes it's maximum, and then let's say this is a temperature, let's say T1, and T2, and another is T3. So what are the distributions for T2 and what? So we must focus on the maximum points. Similar when we plot this the Maxwell-Boltzmann distribution for various temperatures. Right? So we focus on the maximum, how the maximum changes. So first, the one thing is that the area under the curve remain constant. So when we plot this for the T2, this look like we come to this one. What, why, how to connect this maximum? First we draw this, and then I will discuss. And this is, let's say, for something looks like this. now if you plot for the lambda, so for lambda goes to 0, this is dominant. Okay, so same thing for lambda is so focus on the maximum point. So again this is let's see T1, T3, this T1, this is T2. So the interesting thing how to connect this. So in this case, this line times, and in this case we connect. Okay, so let's first derive this and then we'll see how to connect. So for this case, what we okay, so first yeah, from this let's say v t cube equals to constant. So v t cube equals to constant. So what is the v? It's proportional to lambda to the power. Lambda is a wavelength by dimensional analysis. V is a volume and lambda is a wavelength. By dimensional analysis, V is lambda cube. V is a L cube, right? Let's consider a cube with length L. Volume V is L cube. Hello. So L and wavelength are the same. So V is proportional to lambda cube. Lambda is a wavelength. So by dimensional analysis, naively we see that the lambda cube t cube equals to constant. So that means lambda t equals to constant. So this is the one way you can see that the lambda t equals to constant. But to derive the wheel's displacement law, tells that the lambda max times t equals to constant. So this is the naive limit. This is the naive limit. By dimensional analysis we can check this. But explicitly the one displacement tells that the lambda max times t equals to constant. So that means if we plot the black body distribution as a function of lambda, okay, so lambda max where the distribution is maximum at this point. This is the lambda max. For T2 this is the lambda max. For T3 this is the lambda max. Okay. This is the lambda max for T1. This is the lambda max for T2. This is the lambda max for T3. Right? So what the curves look like? This lambda max t equals to constant. That means they are hyperbolarized xy equals to constant. So that means the lambda max and temperature T, they must follow the hyperbolic curve. That's why I have here I plot the hyperbola, the maxima of this curve joining by the hyperbola line. Okay, because lambda max T equals to constant. So in this case lambda max is hold on, just a minute. No, sorry. The temperature is because in this case the lambda max is high, right? So T is small. Oh, sorry, yeah, T is small. Yeah, T3 is small. T2 is high. T1 is high. Yeah. So in this case, right? So this case lambda max is high, right? At this point, lambda max is high because this is the lambda max is high. So T3 is small, right? But in this case, lambda max is small, but T3 is high, such that the product remains constant. Similarly, so they are joining through the hyperbola line. The maximum of this curve to the hyperbola line with the temperatures. But in this case, for u nu versus nu, so you know that the nu equals to c by lambda. Right. There is interesting thing that it is true that nu max is equals to c by lambda max. So we know that the nu equals to c by lambda, but at a maximum point this relations hold. It will be true. How to know? No, inversely proportional, but there is a some, but I mean that the inversely proportional is true, but this is not that the exactly that c by lambda, right? So this relations which holds at maximum points just nu is inversely proportional to 1 over lambda, that is by the through the dimensional analysis, but if there is some constant or not, that I am asking. Okay, so by dimensional analysis you know that the nu max equals to c some constant times c by lambda max. This is also we have, but whatever the constants, we can by dimensional analysis we can use this. Let's say there is some constant, suppose, but still this nu max times, so from this say that the nu max over t equals to some constant. So this constant is not need not be same, right? There is some another constant. So that means nu max is proportional to temperature or some constant times temperature. You need to understand this that the nu max is need not be equals to c by lambda, because at lambda maximum, so this is not a curve that nu, because we are calculating at maximum point what is the lambda max, right? And the nu max is the u nu versus nu curve, what is the maximum. So they need not be related. It's exactly this is c over lambda max. My dimensional analysis is proportional to c over lambda max. That's true, but there may be some factors. So that means this constant and here in this constant is a different constants. Yeah, so this constant is actually calculated for yes. So this constant for in this case the constant value is 2.9 millimeter times Kelvin, and in this case the constant value is 5.1 times millimeter times Kelvin. This constant value is important. It's 2.9, but this is a different constant. Okay, 5.1 millimeter times Kelvin. That's why I'm wondering these things. Okay, but whatever. The main thing is that a nu square is proportional to temperatures, right? So that means that the maximum points. So this is, yeah. So this is for T1. So this is T1. This is for T2, and this is for T3. So they are connected through a straight line. Here is a hyperbola. This line is a hyperbola. Okay. The slope is different. Okay. Here is a connected through the straight line. Okay. Let's take that. Here is a lambda nu max. It's large. Temperature is large, proportional. Here nu max temperature. This is a straight line. Okay. This constant is greater than 0, positive slope. Okay. Yeah, it has become clear. Or any further questions? Okay. So another is thing that suppose the area that asks is the what is the adiabatic invariant quantity for the photon gas? What is the adiabatic invariant quantity for the photon gas? Adiabatic invariant quantity for the photon gas, or quantities for the photon gas. So adiabatic invariant, that means the concept through the adiabatic process. Okay. So once is that the entropy. So entropy constant, which implies that heat T cube equals to constant. So that means heat T cube. Yeah. So heat T cube equals to constant. So heat T cube is adiabatic invariant. Now we can also construct that what is the V, that by dimension analysis V is lambda cube, which is inversely proportional to nu cube. So that means nu cube times V is also constant, also adiabatic. So adiabatic invariant. So these two quantities are adiabatic invariant for the photon gas, that NQ2 and AD2. Another thing we also discussed is the lambda T. Lambda T. So lambda T is also adiabatic invariant. Okay. So now go into the law of thermodynamics, go into the problems related to the thermodynamics. Then we solve one problem related to the kinetic theory of forces. Question is that how much heat required to rise the temperatures, of 1000 gram of nitrogen from minus 20 degree centigrade to 100 degree centigrade at constant pressure. How much it is required to rise the temperatures from 1000 gram of nitrogen, of 1000 gram nitrogen from minus 20 degree centigrade to 100 degree centigrade at constant pressure. Okay. So this is the one part. Second, how much has the internal energy of the nitrogen increased? How much is the internal energy of the nitrogen increased? Third is that how much external work was done? Was done. So the first question, the first part of this, that what is the formula for heat? The heat required. No, first is the questions first. So rise the temperature of 1000 gram of nitrogen from some temperature T1 to T2, right, at constant pressure. So that N times Cp times density. N is a number of moles, and so it's a NCDT, right? C is a specific heat. So here is a constant pressure, that's why we put a CP at constant pressure, the specific heat at constant pressure. And the 1000 gram of nitrogen, so we convert to moles, in moles, and Cp, and the temperature difference. That's the heat. This is the delta T, the heat required. So, so first calculate the. So what is the N? N is the 1000 gram divided by nitrogen. Yes. So 1000 by 28 times Cp. What is the Cp? In terms of, let's say, given the Cv is given. So Cv is given 5 calorie per mole times degree centigrade, and R is, let's assume 2 calorie per mole per degree centigrade. These two things are given. So how to calculate Cp? Cp is Cv plus R, right? So again, we consider the nitrogen gas as one kind of ideal gas. That's why we use Cp minus Cv equals to R. So Cp equals to Cv plus R times delta T. So delta T difference is like 120. We kept in degree centigrade because the Cp and R also in the degree centigrade. So that's cancel. So, this is a mole, so mole cancel. This is a calorie. Sorry, not put here the Cp plus R. So let's say put this. This 7 120 calorie. This 3 down times 10 to the power 4. Right. So first we calculate the moles, and then, so if suppose here is given a constant volume, then we can put a Cv here. Here is a given constant pressure, so that's why we put Cp and the temperature difference. Second part is that how much has the internal energy of the nitrogen increased? The first part, the increase in internal energy, delta U. Now tell me, what is the increase in internal energy? Consider nitrogen gas as an ideal gas. What is delta U for ideal gas? So for ideal gas, delta U is N Cv delta T. For ideal gas, U is a function of only volume. Sorry, U is a function of only temperatures. So delta U equals to N Cv delta T. So Cv means the constant volume, volume independent. So that's what Cv N Cv delta T. This is equals to 100,000 by 28 times Cv times delta T 120. And again, this is a calorie. So now the third is that how much external work was done. So work done delta W L2 minus right? Remember, this is external work done. So our sign convention is that del u del q minus delta w. Right? So this delta w is the external work done. External work was done. So that is the delta w is delta q minus delta u. So just difference. We get so we get that 1000 by 28 times 2 times 120. Yeah, so it is clear. So when you calculate this work done, this kind of things, you must remember the sign conventions. Okay, what do you do is so external work was done. So that's why we use this del q equals to delta q minus delta w. If the external work done is positive, that's why I put a negative sign. If you not put negative sign here, then you get a negative sign in the results. So that means the system is already tells that the external work done. It's clear that the sign convention. If you put plus sign here, then you get delta w equals to minus this. So let's put here plus sign here. That means what is the delta w? Del u minus del q. Yes. So you get a minus sign. So that means this minus sign tells you that the gas is worked on the surroundings. The external work was done. Yes. So here is a question: is that how much external work done? So already tells that the how much external work was done. So that means we just put this value without this sign. The sign already tells this the external work was done. Times sign tells us the external work. But how much this? So if you mark the questions with this negative sign, this is wrong. Because in the question the asks that how much external work was done. So external work was done, that means the negative sign is already taken care of. This. Okay. So now the second question. Is that let's say two systems with a heat capacity. Just recapitulates the old things that we learned so far. The two systems we'll discuss this too many times. So the two systems. So this is the heat capacity C1 and this system has heat capacity C2. Right? And let's say this is a T1 and we do not know this is a T2. This is not known. So calculate the final temperatures. The final temperature is given is Tf. So two systems with heat capacity C1 and another is a C2. Now connect. So and finally they are thermally connected, and finally there is a common temperature Tf. So Tf is a final temperature, and T1 is the temperature of first system, temperature of first system. Calculate T2. What is the second? What is the temperature for the second system? What is the temperature for the second system? So how to calculate? So consider, assume that total energy is conserved. Total energy is conserved for the combined system. So of the combined system, total energy is conserved. Combined systems. Total energy of the combined system is how to calculate T2. So that means the heat released from the system 1, energy is conserved according to the conservation of energy. That heat released from the system 1, which must be absorbed in the system 2. Okay. So again, what is the delta Q? It's N, heat capacity for the system 1 C times delta T. So heat released from the system 1, C1 times T1 minus Tf what is the heat absorbed in the system 2? C2 times plus Tf. Why? Tf is the common temperatures. So this is heat absorbed and this is released. Let's say put negative sign here. Right. According to a sign convention, that heat released, we put a negative sign, and heat absorbed, get a positive sign. Oh, so this is a delta T, right? It's a difference in the temperatures. So why you say that? Why you say that the T2 plus T? Okay, let's say initial this is a temperature T2, but you don't know. You calculate this. And there is the final temperature Tf. So the heat absorbed is Tm minus T2 because that's the amount of heat released. Yes. So then you calculate this T2. Just manipulating this algebra, this C1 and C2. If C1 by C2 minus 2 plus this is the difference. The opposite way you can ask that if let's say T2 is given, what's the Tf? So the overall picture is that how to calculate these things. Okay, that one thing is given, you calculate the others. Sign convention is important. If you mistake in the sign, then you end up with a different results. So if not clear, then ask. I will explain again. But sign convention is clear. If you mistake, yeah, let's say if plus sign, then you got a different result. Right? So that's why I am doing this types of examples again and again. So you must clear the sign conventions. Right? So why we put negative sign? Why we put positive sign? Why we write this T1 minus Tf and T2 minus Tf? Then if we put here plus sign, right? So if we put here plus sign, so you end up with a different results. That is not correct. Okay, so now another thing is that, the question is that there's a steam turbine is operated with an intake temperature, operated and intake temperature of 400 degrees centigrade and exhaust temperatures of 150 degrees centigrade. So what is the maximum amount of work the turbine can do for a given input Q? That what is the maximum amount of work the turbine can do for a given heat input Q. For a given input Q. And under what condition the maximum achieved? Second is that under what condition is the maximum achieved? So that means any engine operate. So what is the schematic diagram? That this is a 400 degrees centigrade and there is a engine operate and the lower temperature is exhaust temperature is 150 degrees centigrade. So this is TH, this is TL and this is W. So what is the work done? So we calculate the efficiency, right? It's eta 1 minus TL over TH. So which is equals to W over Q in. This is Q in. So the heat input is Q, maximum amount of work for the turbine. So when we write this formula, beta, so this is only for the Carnot engine, right? That means the reversible. That means the reversible. So in general, for the Clausius inequality, Clausius inequality is that the Q1 by T1 means that so QH, TL, so QH over TH minus QL over TL is less than equal to 0. Now the work done W, just QH minus QL, which is less than equals to 1 minus TL over TH times QH. So that means this is the maximum work done. This is the work done. But I know from the Carnot efficiency, so this is the work done from this easy work, as well that W equals to QH times 1 minus TL over TH. The maximum work done is that. So if the heat input is Q, then W equals to 1 minus the maximum work W max, 1 minus TL over TH. So we know that TL is 150 and TH is 400. So 150 over 400 times QH is Q. Okay? So the heat input is Q. So you get that the 0.37 Q. This is the maximum amount of work done. Now the second question is that under what conditions the maximum achieved. So that means that this Clausius inequality. So there is a inequality sign. So when the equality hold for the reversible cycle, because we choose a reversible heat engine and we calculate exactly equal, this W equal to QH minus QL. But here is a unequal. So that means for reversible cycle, the work done is equal to this. That is the maximum. Understand my point? Yeah. So for reversible cycle, that means under what conditions the maximum achieved. So when this steam turbine, operate reversible. Any kind of engines on kind of cycles, right? So if the cycle is reversible, then the maximum amount of work is achieved. So that means if the cycle is, hello, if you have any other questions, please mute yourself. Hello. Okay, so if the cycle is reversible, then the work done is maximum. then the work done is maximum. Just a moment. Okay, so if the cycle is reversible, then the work done is maximum. That is, the reversible engine can it achieve a maximum work. The irreversible engine is always less work is compared to the reversible. The another question is that so let's say a building at a temperature T. So a building at a temperature T is heated by an ideal heat pump, which use the atmosphere at temperature T naught. Which uses the atmosphere at temperature T naught as a heat source. So the pump consuming power W, the pump consume power W, and the building uses heat at a rate alpha times T minus T naught. What is the equilibrium temperature of the building? What is the temperature of the building? Yes. So here we consider the heat pump as a heat source. This is the different from the Carnot engines. Okay. So a building at temperature T is heated by through the heat pump, ideal heat pump, and I consider it as a heat source. So they kept at constant temperature, atmospheric temperature T naught, the heat pump. Now the pump consumes power W, and the building loses heat at a rate alpha times T minus T naught. So what is the equilibrium temperature of the building? So let's say the equilibrium temperature Tc. equilibrium temperature TE. So heat is given out by the pump at the rate. So heat pump. So Q, that is the heat given out by the pump. Heat given out by the pump. Q1. That's it. Heat given out by the heat pump. What is this? This Q1. What is the efficiency? The efficiency is W by Q1, right? So that means that this is a work done by eta. Eta is the efficiency. The efficiency. So this efficiency, what is the efficiency for the heat pump? Efficiency for heat pump. One minus heat pump kept at temperature T0. Now the temperature is TE. So T0 by T. Okay. This one is clear. So now this heat given out by the pump and the building. So heat given out by the pump, this W1, and the building losses heat at a rate this. So that means this Q1 is equals to alpha times TE minus T0. So this is TE, the equilibrium temperatures, then the building loses heat, and this is pumping to the building. So at equilibrium, this Q1, the heat pumping to the building, and is equals to the building losses heat, alpha times T minus T. This implies that W equals to alpha times T, alpha by T, okay, times T minus T0 square. Now how to solve T? So this point is clear, right? So at equilibrium, the heat pumping to the building is equals to the building loses heat. The building loses heat at a rate with alpha times T minus T0. So now at equilibrium temperature T equals to T, the what amount of heat loses by the building, that is exactly pumping to the buildings. Okay. Hello. Okay. So now how to solve the T equilibrium temperature from these equations. So the easy way to solve this, let's say T minus T naught x. Let's say this x. So that means x square equals to W. First write this in terms of that T minus T naught square equals to WT by alpha. So now here we add this and subtract this plus W not over alpha. So now consider this T minus T. What's this? X square minus W over alpha x minus W T over alpha equals to 0. Then quadratic equations. So there are two roots, W by alpha plus minus W by alpha square minus 4 times A times 6 plus 4 times W T naught over alpha divided by 2, right? So it is equals to W over 2 alpha plus minus W over 2 alpha square plus W T naught over alpha. So now, so which is equals to T minus T naught. So now which sign is possible? So this T is greater than equals to T naught. It's the equilibrium temperatures. Right? So this T, so T is greater than equals to T naught. That means this must be greater than equals to 0. It implies that T minus T naught is greater than equals to 0. So which implies that, so here is a W by 2 alpha, right? And here is a W by 2 alpha square. So this quantity must be, so this W by 2 alpha square plus W T naught by alpha, this must be greater than equals to W by 2 alpha. This is just for the, this is just looking that here is a W by 2 alpha and here is a W by 2 alpha square. So but here is, due to the extra term, this must be greater than equals to this, must be greater than this. So that means T minus T naught greater than equals to 0 for only positive sign. The negative sign is not possible. Okay. This part is clear. Yeah, because otherwise it gives a negative sign. So then what is the values of T? It's T naught plus W by 2 alpha plus W over 2 alpha square plus W T naught over alpha. That is your equilibrium temperature. I'll take 5 minutes extra, so I do one more problem and I stop. So this problem is important. Yeah. So the next problem is that so a body of constant heat capacity, let's say Cp, body of temperature Ti is a so body had a constant capacity Cp and the temperature Ti is put into contact reservoir at temperature Tf. Equilibrium between the body and the reservoir established at constant pressure. So, equilibrium between the body and the reservoir established at constant pressure determine the total entropy change. Change and prove that it is positive always positive. Okay. So okay, so what is the question that a body at constant heat capacity Cp and a temperature Ti it would contact with a reservoir Tf. So that means, so let's say there is a reservoir. So this is a big reservoir at temperature Tf. It's thermal contact with a body. Let's say this is Ti. Okay, so this is a body. And this is a reservoir. Put in thermal contact. Equilibrium between the body and the reservoir established at constant pressure. Right? So equilibrium at constant pressure, equilibrium established. So determine the total entropy change and prove that it always positive. So first we calculate the total entropy change means the entropy change of so the entropy change of body plus entropy change of reservoir. So what is the entropy change of body? So entropy, the change of entropy of the body. First case, change of entropy of the body is delta S1. So now the body's temperature Ti to the reservoir temperatures, because the reservoir is that the temperature is constant. So when the equilibrium achieved, that means the body's temperature is equal to the reservoir temperatures. So Ti to Tf, and this equilibrium achieved through the constant pressure, that's why I put the Cp times dT by T. How do I know this? Because we know that del Q equals to C dt, right? You consider 1 mole of gas, and this del Q equals to D delta S, sorry, D ds equals to C dt. Now we put this from there. We know this delta S, it's Ti over T, the integrate Cp dt. So this is nothing but Cp ln Tf over Ti. Now second, the change of entropy of the reservoir. Change of entropy of the reservoir. Can you tell me what is the change of entropy of the reservoir? just a delta Q by Tf, because the reservoir kept as always at constant temperature T. That's why there is a no integrations. Okay. Because the reservoir temperature does not change. So the change in entropy of the reservoir is just the change in Q, not the change in temperatures. So here we have integrate over T because the body's temperature changes Ti to Tf. Here in the case of reservoir, this is the important. In the case of reservoir, the temperature does not change, only the change in Q. So the change in Q is Cp times Ti minus Tf over Tf. Because the reservoir, from the reservoir the heat is released, right? And this heat absorbed in the body. Okay. So heat is released. This means delta Q equals to minus Tm minus Ti. So here is the minus sign I have put into. So I write here Ti minus Tm instead of Tm minus Ti. This minus sign is already included here. So that means the total change in entropy delta S1 plus delta S2. So Cp times Ti by Tf minus 1 plus Ln Tf by Ti. This is Ln. So now how to show this delta S is greater than 0? So there is a inequality that ln x is always greater than equals to x minus 1. Yes, ln x is always sorry, this inequality. Yeah. Or okay, let me check. Let me check. Yeah, so the ln x is always less than equals to what is the inequality? Yeah, so ln x is always greater than equals to this inequality. Ln x is greater than equals to 1 by 1 over x. So you can prove this inequality. So use this. So we can tell that the delta S total is must be greater than equals to. It's always positive one. Okay. So when we calculate the body, the change in entropy of the body, we integrate Ti to Tf because the body temperature changes. But when you calculate the reservoir temperatures, the reservoir entropy change, the change in entropy in the reservoir, it's just delta Q by Tf. In this case, there is no integrations because the reservoir temperature does not change. So that is the importance. And use this inequality, you have to solve this. Okay, it is clear now, right? Okay, so then I will stop here, and this is the last session, so there is no more sessions. And if you have any further questions, so you can ask in the discussions forum before the exams. So yeah, so you can ask in the discussions forum for the exams, or comment in the YouTube videos. I will try to answer these questions within time. Okay, all the best for your exams. If you are appearing for the exams, right? Okay, when is your exams? Yeah, so if any questions in between, so you can ask in the discussions forum or in the YouTube comment sections. Okay? So I will try to answer those questions. Okay, once again, all the best for your exam. Yeah. Okay, bye bye.